How's everyone doing today? Any questions, concerns for you guys before we get started? All right. Main goal for today, we're going to conclude chapter 10 by doing some math for the concept we introduced at the end of last time. That was the Doppler effect. So we're going to use the formula for it, make sure that makes sense, and then that'll be the last new thing we cover, the last formula I'd like you to be able to use on the exam. Speaking of the exam, I have updated both the list of concepts in the exam tab on Brightspace that you should be familiar with, and also the practice exam. So I'll say I have one last tweak to make on the practice exam. I just remembered it this morning. There's one last concept question I want to attach at the end. Once I make that change this afternoon, it'll be the draft that I'd recommend you use to study, and I'm going to upload a key for it this afternoon. Once we're done with chapter 10 today, we can talk about that, exam prep, and then also Monday will be a day where we'll make sure everyone feels comfortable before the exam happens. Speaking of the exam, I don't know why, but I like having a calendar when I'm talking about time and dates. Today is December 1st. Happy December, everyone. Last day of class is Monday the 4th. There's no lab this week there's no lab next week, if that needs to be said. No lab next week. Monday will be the last day of class. Again, we'll spend that day making sure everyone's feeling ready for the exam. And I do have one last demonstration to show you guys. I didn't have time to set it up for today, but it'll be cool, I promise. Tuesday is the day that all assignments are set to be due, officially speaking. So that's the day that I've got the homework set to, and that's also the day that I would like makeup labs turned in by if you're doing those. Officially, that's the last day things can be due. Unofficially, I need the makeup lab by the 15th, before the 15th, because that's when grades are going in. Then, exam season. This course's exams will be offered 2 different days at 5 different times. Those are now listed over there. I've added 2 since the original announcement. I'm going to email that out so you have the list written. The 5 slots, 3 of them are on Thursday, December 7th. One is at 8:30, then 1:30, then 5:30. I'm just going to be here all day that day. Friday, the 8th, there will be one at 8:30, one at 5:30. Now, Dr. Owens is going to be proctoring the Friday ones for me. Something's come up and I have to be out of town. So I've added the Thursday ones for flexibility, and so that I'll be in the building all day in case you have questions or anything you need for study purposes that day. So come to any one of them that best works for you. And again, I'm going to be here all day Thursday. Come ask me study questions. I'm going to be camped out probably in that chair from 8 a.m. to 9 p.m. So come find me for anything you need. And pick any one of those you want to take your exam. Any questions or issues here at the start? All right. In that case, let's finish up chapter 10. As I said, the concept we introduced last time is called the Doppler effect. This is what is physically responsible for that meow effect you get when something moving very fast passes you. And the frequency of sound you hear from it changes from high to low in that moment it passes you. The nee part is higher pitched and the ow is lower pitched. Forgive my impressions. But meow is a very technical term as it relates to this. The reason this happens is because when sound waves are being made by a moving object, that kind of changes the effective wavelength of the sound waves, because if you are racing towards the wave you just made, the next wave comes out closer to it than it's supposed to, and that kind of drives down wavelength. And if you drive down wavelength but keep wave speed the same, frequency rises, as we discussed when looking at the wave speed formula. If wave velocity remains the same, because you can't really change the speed of sound by moving. What you're just doing is bunching the sound waves up together. If speed of sound stays constant And wavelength gets smaller, frequency has to rise to accommodate. And the inverse happens when something is moving away from you, because then the next wave comes out further away than it's supposed to from the previous one. That stretches out the wavelength and drives frequency down. So again, meow, ni is higher pitched, the ow is lower pitched. And we're going to prove how that math works today using this formula. Formula says that the frequency you observe, this is what you actually end up hearing, is equal to the original source frequency, so the actual frequency that the object is supposed to be making. Most sirens are supposed to make a specific hertz of noise. That device doesn't do anything different when the vehicle is moving, but what you hear ends up changing. Whatever frequency the object is supposed to make goes there. The frequency you normally hear if everything was sitting still. So F source is the normal frequency that the source object, source of the sound, is supposed to be making. And that frequency gets adjusted by this weird looking fraction here. This fraction is, on the top part, V wave. This is actually the velocity of the wave normally. So the speed of sound would be plugged in for both of these V's. It's the same velocity, there's no subscript. It's just supposed to be V wave in both positions. The top part of the fraction is V wave plus the observer's velocity. And usually you are the observer if you are hearing something. So that would be your velocity going up there. Then underneath, V wave minus the source's velocity. And in the case of an ambulance, that would be the ambulance itself, since it's making the noise. And what this fraction does is it kind of adjusts this frequency based on the relative velocity between you and the source to change the sound you actually hear. So this fraction ends up being, it becomes a fraction either bigger than 1 to drive the heard frequency up, or smaller than 1 to drive the heard frequency down. And we're just going to show how the math for that works. Any questions before that? All right. I keep talking about ambulances, so let's put some numbers to an ambulance. We're going to say that this particular ambulance's siren is built to output 6,000 hertz sound. That's the frequency you're normally supposed to hear when the device is turned on and when it and you are standing still. And before I actually do anything else, I actually want to use this formula real quick to show what happens if both the observer and the source are standing still. We are going to be the observer, because we are the organism with sound detecting organs, and the ambulance's siren is going to be the source. And if we are both standing still, we aren't moving, and the ambulance is parked, our velocities would both be 0. The way that this would work in the formula is you plug in a 0 for both our velocity of the observer and the velocity of the source, and that would not end up changing either part of the fraction. The first part on both the numerator and the denominator is wave speed, speed of sound. For simplicity's sake, we're just going to keep that at 343 today. So if that's the speed of sound, if we are both standing still, it's going to remain 343 on both the numerator and the denominator. And as a result, this fraction would just be 1, right? Anything divided by itself. So 1 times the original frequency would spit out the original frequency again, proving that if neither you nor the ambulance is moving, you should be hearing 6,000 hertz, which again is a tone equivalent to some human speaking voices. The ambulance is just really loud about it. So if nothing's moving, we plug in zeros there, and you should get the same frequency in and out. Now let's see what it does when something is moving. We're going to say that this ambulance can drive at 30 meters per second, and first we're going to see what that does when it's moving towards you. So we're going to stand still, our velocity is 0, and velocity source, since the ambulance is the thing making the noise, is going to be 30. And now we have to plug that in for V source into the formula. Now, velocity is a vector. We do care about direction, but this formula uses direction a little bit differently. Rather than plus meaning, positive axis and negative meaning negative axis, we want to plug in a positive velocity if the object is moving towards the observer, and a negative if it's moving away from the observer. Officially, north, south, east, west doesn't really matter. What matters here is direction relative to each other. In this case, if the ambulance is driving towards us, we want to keep that number positive, because it's drawing nearer to us, and we'll see how that drives up frequency. Now note, the ambulance is the source. So we're going to put that positive 30 here, and it's going to end up with a negative sign in front of it. That's on purpose. We want to plug in a positive so that that negative remains. Our velocity is 0, speed of sound is still 343, and now for the speed of the ambulance, it's moving at 30 towards us, so we plug in positive, and that negative sign remains. We want that there on purpose. And what that's going to do is, it's going to create a fraction bigger than 1, since the denominator is going to shrink. The numerator stays the same, because we're just adding 0. The denominator shrinks to 313. So that fraction is now bigger than 1, and that multiplied by 6,000 is going to drive up the frequency, which, as I mentioned, is what happens when two things draw towards each other, because that bunches the wavelengths up, wavelength down, frequency up. So shrinking the denominator drove up the frequency we hear, and I believe that should give us a final observed frequency of 6,575 hertz. An increase of 575, about 9%. And that is a difference perceivable to the human ear. You could tell a 500 hertz, a 600 hertz difference. If you want to test that for yourself, if you haven't done the makeup lab, again, it's optional, but if you haven't done it, there's a link in it to a sound test that'll play every frequency of sound a human can hear, and you can click between parts of that video to physically hear the difference between 6,000 and 6,600, just to prove that there is a difference that you could detect. So this already increased the frequency to a measurable degree. And again, as long as the objects draw nearer each other, the frequency should rise. Questions? All right. Now we're going to have the ambulance driving away from us and show how that drives frequency down instead. The only real difference here is the ambulance's velocity is still 30 and ours is still 0, but if the ambulance is driving away, we want to plug in negative 30 instead of positive 30. That negative will cancel with the negative that's already there, and that's going to end up making the denominator bigger, making our fraction smaller than 1. So now it's 343 over 373. And our perceived frequency is going to change to, I think, 5,517 hertz. The last 2 times I did this calculation today. And that is about 500 hertz lower than the original frequency, which again, you could detect. So if the objects move farther apart, the fraction becomes smaller than 1, drives frequency down. And the really big shift is between these two frequencies, because the two numbers we just calculated are about 1,000 hertz apart. And that's why you get that really big difference right as the vehicle passes you. It goes pretty much suddenly from the bigger number to the smaller number, a difference of 1,000 in a split second, because the ambulance is only adjacent to you for a split second. So the difference between these two is the really big part that actually forms the meow. good? Questions, concerns? All right. Real quick, the last thing I want to do with the math here is just prove that this works even if the ambulance isn't the thing that is moving. So instead, I'm going to change this to a weirder hypothetical scenario. We're going to park the ambulance in place. So the ambulance's velocity, the source's velocity is going to be 0 this time. And now we're going to be the ones running at 30 meters per second. We're first going to run towards it and then away from it. Maybe you're a superhero carrying people to the ambulance. Maybe you're just an ambulance chasing lawyer. The context is up to you. Here's my eraser. So I'm just going to change what's on the board. You shouldn't erase your notes. You should write down new lines. What this is going to change is, now the source is 0 and the observer is 30. So we're going to kind of switch the positions that these get put in. Now the 30 is being added to the top instead of subtracted from the bottom. And that's still going to create a fraction bigger than 1. It's just instead of 343 over 313, now it's 373 over 343. But it's still bigger than 1. It won't create the same frequency as the ambulance moving towards us instead, but it's still a higher frequency. I think that drops it to 6,525, which might not be significant enough for you to notice the difference between. But the main thing is it is still a similar caliber higher, even though we're the ones moving. And that's because rather than the waves being made closer together, we are receiving them sooner than we're supposed to. If you're running towards the source of the sound waves, they will collide with you in your eardrum sooner than they're supposed to, still bunching up the wavelengths, still driving up frequency. Bless you. And the inverse still happens if you are instead running away from the ambulance. Because now we plug a negative number into the top. So now we subtract 30 from the numerator instead of adding 30 to the denominator, and we get 213 over 243. And that, this one I don't remember, 5,475 approximately. So a similar reduction in frequency, even though we're the ones moving. And so that means if you run really fast past something, you can generate the meow yourself. If you have a speaker and just park it in the middle of a field and run towards and past it as fast as you possibly can, you can generate this yourself. I will say though, the difference is less extreme at slower speeds, because if a human can run at like 3 meters per second, maybe 5 meters per second, you'd only be adding or subtracting, 3 to 5 from this fraction, from the numerator or the denominator, and that's going to make the fraction closer to 1, and that's not going to adjust the frequency nearly as much. You get this the most at higher speeds fractionally closer to the speed of the wave. So that's why you don't often notice it much, if at all, when you are just moving around, and you only really notice it when a fast thing is moving near you. But if you move as fast as you can and listen as hard as you can while running, you can try to make it generate it yourself. And again, regardless of which one's moving, as long as two things are drawing nearer each other, frequency goes up, and further apart, frequency goes down. Questions? All right, so that's the last piece of math I'd like you to be able to do for the exam. There's one sound question on it, because it's the last thing we did. And that one sound question would ask you to use this in a very similar way as we just did. Before we close chapter 10, before we close the book, functionally speaking, I just want to point out a couple other places where this comes up in life on Earth. I've already mentioned that this is responsible for that effect when a vehicle passes you, but this is also the principle behind it. Pretty much any human-built form of sonar or radar detection, something that can tell you how fast something is moving from a distance. Say I watched a lot of car shows, so I've seen a lot of, within those shows, people using like a radar scanner to determine the speed of a car from a distance, so that you don't have to actually be in the car watching its speedometer. That type of technology, what the device does is it emits radio waves at the object, and it knows what frequency it emitted. Then the radio waves strike the object and bounce off. Because as it turns out, waves just like echoing and reflecting off of things. They tend to just do it all the time. Even with this standing wave that I've been using all week, the speaker makes the wave, sends it down to the pulley, and then it bounces back of its own volition. Waves just reflect off of things as a natural habit. But the way that technically works is when the wave hits something, the object absorbs the wave as energy and then starts shaking at the right frequency to emit it back. So every echo is technically a freshly generated sound wave. It's not the same wave you made. It's a new one that is generated by whatever the wave struck. And for that reason, technically when the radio wave hits the vehicle, it becomes the new source because it's re-emitting a new wave. And when it is now the new source, its velocity is going to change the wave. And so the radar scanner is going to receive back a different frequency than it emitted. So it knows what frequency it emitted, it's measuring the frequency it receives back, and it's able to use this formula to figure out the speed of the car. Every form of human-built radar detection uses this, whether it's for race cars or, I mentioned sometimes you hear Doppler weather radar. They use this on literal thunder clouds to see if they're moving towards or away from you. So cloud speed detection is the same thing. That's why it comes up in the weather. I'll also point out that this means that this does work with light and electromagnetic radiation, not just sound, because radio waves are a form of electromagnetic radiation like light. If you wanted to do this for radio waves or light waves, you would just use the speed of light instead of the speed of sound. And then the differences are really teeny tiny unless you're moving at relativistic speeds. But it works with every type of wave. They might even use it in earthquake tracking. Or they might, they send pulses into the ground and measure the frequencies they get back sometimes. So seismic waves work too. I had another point. What was I going to say? Oh. It's not only human-built things that do this, animals do it too. Because every animal that uses sonar, bats, marine mammals, anything like that, does this math in their head. They are not only, when a bat screams, it's not only listening for how long it takes the echo to come back, it's listening for what frequency comes back. Because once again, it knows what frequency it's screaming at. And if it hears a different frequency, it means that whatever it bounced off of is moving. And it can tell lower frequency, further apart, higher frequency moving towards me, and do the basic math for how fast is it, do I need to turn now? So animals are pretty smart. They can do algebra. So I find that neat anyway. And that's the end of chapter 10. How do I feel? I feel like I'm asking that a lot today. All right. Let's move on to try to discuss, we will discuss the exam in as definite terms as I am allowed to give you. I said again that the final exam tab has been updated. The tab itself lists every concept that I would want you to be able to use on the upcoming final. It's basically just the test 1 list and the test 2 list added together, which is why I do recommend looking at the old tests to help study. The only additions from the two lists are these three things at the end here from what we've done this week. So, in definite terms, the three Chapter 10 sound-related things I want you to know for the exam. One, I want you to be able to tell me what a sound wave is in that it is a mechanical longitudinal wave. Mechanical meaning it requires a physical medium. Sound needs air for you to be able to hear it. And longitudinal, which is to say that it shakes this way, not this way. This is transverse, and that's what light is, not sound. Sound oscillates in the same axis as travel. It's a pulse forward and backward in the same direction it's moving in. So, what is a sound wave? Thank you. Thank you for humoring me. Yeah, when I ask, what is the nature of a sound wave? This is the answer. It's telling you mechanical and longitudinal. Second thing, wave speed formula. I had it on the board. Wave speed equals frequency times wavelength. If I tell you speed of sound is 343 and you hear a 500 hertz noise, what is its wavelength? Be able to use this. I would also recommend being able to compare this to the other velocity formula. Again, you can use the speed of sound to figure out how far away a thunderbolt was, for example. So, wave velocity, frequency times wavelength, but it's still velocity, so delta x over delta t still works. Lastly, Doppler effect, the formula from today. If I tell you that you are moving towards something, use the formula to adjust the frequency heard. There's one sound question that encapsulates these few concepts on it. It's not a big part of the test, but I want to make sure that you're aware it is there, and I put it on the practice test. The exam itself is 16 questions, so slightly shorter than test 1 and test 2 fused together. That would be 18, this is 16. Of those 16, 5 are concept short answer, and 11 are math, which is a lower math ratio than the other tests. The other test was 8 to 7. Sorry, 2 to 7. I want to make it clear again though, one of those concept questions is going to be identifying the laws of motion. You still have to be able to do that. So, same kind of question on test 1, just I've rewritten all the statements and thrown in different dummy statements. So, you still have to pick them out of a lineup. But that's one of the 5 concept questions. The math-related questions will all refer to concepts and formulas on this list. And the practice test, which is almost totally updated, I just want to add one more thing to it, has 23 questions on it, featuring a mixture of both concept and math. Again, practice test is longer and more difficult than the actual exam. This is 23 questions, the exam is 16. And I've written the exam in such a way that takes into account that you have a fixed amount of time to do it. My exam questions are not meant to stump you, they're meant to see, can you do this can you use the formula in the allotted amount of time. And I recommend looking over the practice test. I'm going to upload an answer key for it this afternoon. So looking over it over the weekend, we can look over it on Monday as well. Monday will be dedicated to making sure everyone's questions are answered, making sure everyone's comfortable with the exam before we end classes this semester. I'll also, again, have a demonstration to show you on Monday. I'm excited about it. It's the coolest machine that I have in the closet. So, if for no other reason, come to see that. How you guys feel? All right. At this time, we can, floor can be open to any questions you guys have as they relate to homework, quizzes, labs, practice exam, etc. But we can also close down here if there's something on your minds right now. So stick around if you have questions. But if you don't, have a wonderful day.
If we do that makeup lab assignment, will we still get points on it?
Yes.
Even if we win it? Okay.
Yes. If you didn't miss any labs, doing the makeup lab will either fill in a low grade or earn extra points on one.
Awesome. I appreciate it.
I appreciate you guys, I want you to know that. Even if you don't need to do the makeup lab, I recommend it, and the sound test is, at least link yourself to the sound test to see how good your ears are. It's useful information.
Okay, I said they can both be reflected.
Ah, yes, good.
Okay.
Wonderful.